this is going to work. Okay. Where is this? Okay. Dynamic programming. All right. So dynamic programming. Following our discussion of LP or linear programming, dynamic programming is another technique which has broad applicability. Some of you may already be familiar with dynamic programming. This is, again, as the case with LP, a general type of approach to problem solving. The paradigm itself, or dynamic programming, is some kind of an algorithmic paradigm where the problem is solved by identifying a collection of subproblems and tackling them one by one. Smallest first. So we're using answers to smaller problems to try to figure out larger problems. And what I want to do now is go through, or in this second part of the lecture, go through just some examples. I think that's the best way to kind of get a feel for what we mean by dynamic programming. So the technique is to make a sequence of related decisions and systematically find the optimal solution. This is a generalization of recursion. As I said, we'll go through some examples. Sometimes it's difficult to recognize when dynamic programming can be applied. What we have to be able to do is define what a subproblem would be. The subproblem has to be also of the same type as the overall problem. And the idea is that we construct these subproblems which are independent. So if we try to, as I said, go from this, from solving smaller problems to finding an optimal solution to an overall problem. The main idea, again, is to start with a small part of the problem, find the optimum, then systematically extend the problem. So we can talk about a bottom-up approach, which would be the opposite of branch and bound. And here I just want to refer back to this optimality principle, where we know that any sequence of optimal decisions is also, in the sequence, we have an optimal solution to the corresponding subproblem. What a key point is that in a given state, so if we're solving a subproblem, subsequent decisions don't depend on previous ones, just on the current state where we are now. As I said, we'll go through some examples to look at these different characteristics. For example, if we look at a shortest path, hold on just a second, let me duplicate so I get my pointer back. Just 1 second. Okay, now you see the pointer. Okay, if we have this shortest path, then we know if this is the optimal path from D1 to Dn, then this is also the optimal path from D1 to Di, and so on. So we're going to actually look at try to find identify again these subproblems which can be used to solve this greater problem. As a first step, let's look at an example of this shortest path. Let's say that we have this direct acyclic graph that we have over here, which I've shown over here. What we can do is we can linearize this graph. We're going from left to right, so we can arrange everything on a line. All edges go from left to right. And let's say that we want to find the distance, figure out the distance or the shortest path from S, which is all the way on the left, to all other edges. So we want to find the distance, the minimum distance from S to all other edges. Assuming, again, we have these branches that we drew based on this directed acyclic graph. Let's look at an example where we're trying to find the minimum distance to node D over here. So the shortest path from S to D, we know has to go either via C, so either via C or via node B. So there are no other ways to get to D. So the distance to D is going to be we can say that it's going to be the minimum either of the distance to get to B plus 1, that's this branch or this edge over here, or the minimum distance or the distance to get to C plus 3. Right, so we're trying to find the minimum of those two. If we calculate from left to right, when we get to a certain node, C, A, B, and so on, we have actually already solved all of the information that we need to calculate this minimum distance to V. So if we look at Just the formulation, if V is our set of nodes, E is our set of edges, UV is the weight of edge going from U to V. First, we initialize all distance values to infinity. If we start at the beginning, so the distance from S to itself is 0, and we solve in linearized order these sub-problems, let's say. What we're looking at is trying to find the minimum distance. So for all nodes, for all edges coming into a certain U, plus, so if U is an edge that is connected to V, we find the distance to U plus the length or the edge distance along edge U to V. So what we're actually doing is that this algorithm is solving sub-problems, and we start with, as I said, going from left to right, the smallest sub-problem, and iteratively solve larger problems. In realistic cases, such a directed acyclic graph is actually implicitly given. These nodes themselves represent the sub-problems that we're trying to solve. The edges represent their interdependency. So if we have to solve sub-problem B first, then in order to get to problem or to solve sub-problem A, then we have an edge between B and A. So this notion of this acyclic or directed acyclic graph, which can then be linearized and solved from left to right, is a good example of how we can solve these different sub-problems. Let me just show an example of let's say, a longest increasing subsequence. Okay, I think I have it open over here. Okay, let's say that we are trying to find, so we have an input, as an input, a sequence of numbers A1 through AN, and we're trying to find an increasing subsequence where the numbers are getting strictly larger, and we're trying to find the greatest length, so the increasing subsequence of greatest length. So as an example, if we have these numbers over here, the largest increasing subsequence would be going from 2 to 3, 3 to 6, 6, 9. So 2, 3, 6, 9. In order to understand the solution space, we could create a graph of all allowed transmissions. So for a certain node I and its input element AI, we can add directed edges that wherever AI and AJ are allowed to be consecutive elements. So for example, I can go from 5 to 6, I can go from 6 to 9, 6 to 7, and so on. So I could keep drawing, so from 2 to 6, 2 to 3, and so on. So I could draw all of these edges, and the problem would be to try to find the longest path in this directed acyclic graph. So we have this graph, we have a certain number of nodes and edges. Find the longest path. How can we formulate this? So if we go from J, or J goes from 1 to N, these are, as I said, we have AN input numbers. Lij, or L of J, is going to be the length of the longest path ending at J. That's going to be 1 plus the maximum length of the path to node I, which is the previous node. So if I get to I, then plus 1 to get to J. So Lj is 1 plus the maximum L value of its predecessors. So the predecessors in this sequence. If there are no edges that go into a certain J, then we take the maximum over an empty set. So we're trying to keep track of the next to last node on the longest path to J. What we see here is that we have, again, this sub-problem of trying to find this longest sequence path. The idea is that we're trying to define this collection of sub-problems that we can solve in a single pass. So the ordering of the sub-problems and the relation that shows how to solve a sub-problem gives us actually the answers to these given answers to smaller sub-problems. That's what we're trying to actually do. The question, of course, is what are these sub-problems, and that's, again, depends on the actual solution that or the actual problem that we're looking at. Okay, let me go back to the slides. Another example is trying to find a minimum number of coins that adds to a sum S. Again, as I said, I want to go through some examples that just illustrate these different sub-problems that we can try to solve. Let's say that I'm given n coins. Okay, so a certain number of coins. Each coin has a value, V1 to Vn. So let's say that these are some euros or kunas or whatever. We have one coin has a value of 1, 2, 5, 3, whatever. We're trying to find the minimum number of coins, the sum of which is S. So we can use as many coins of one type as we want. And we're trying to, we have defined a certain sum that we're targeting, and we're trying to find the minimum number of coins that will give us that sum. How can we now look at this as in terms of dynamic programming, or try to find some kind of sub-problems? We defined this notion of a so-called state, where we find a solution to a state that helps us then find an optimal solution to the next state. So let's say that we want to find a solution for a sum which is less than the sum that we are actually targeting. So we'll find the minimum number of coins for a smaller solution, a smaller sum, and use that then to try to find an optimal solution finally for the final value of S that we are looking for. Let's just look at a very brief example. I think I wrote it out here. Hold on. Okay, let's say I have 3 coins. Okay, 1, 2, and 3, and their values are 1, 3, and 5. So these are the actual values of the coins. The question now is what is the minimum number of coins I need to obtain a sum of 10? How we can formulate this is, and I just tried to illustrate this like this. So let's say that I have a sum of 10, and I consider coins 1, 2, and 3. If I consider coin number 1, I can look at, okay, it has a value of 1, right? So if I subtract that from this overall sum of 10, I get to the sum of 9. So the question is, what is the minimum number of coins for sum 9? And let's say I have already found that previously. Let's say that's 3. If I add this 1 coin, which has a value of 1, if I add this 1 coin, then the minimum number of coins for sum 10 is going to be 1 plus the minimum number of sum 9. So 1 plus the 3 that I need for sum 9, that will give me 4 coins. And I'll go back to on the slides, you have written out the actual formulation, but this again, just as an example. If I consider now coin number 2, which has a value of 3, then the question is, that's 1 coin, but it's worth 3. So the question is, how many coins, what is the minimum number of coins to get a sum of 7 plus 1, right? So that's plus this 1 coin will give me a sum of 10. But what is this minimum 7? And let's say again that I've solved this previously. I found that to be 3. I don't care about this solution anymore. I'm just using now this solution to this sub-problem. I add this one coin over here, and I get the sum, the minimum number of coins for sum 10. If I consider coin number 5, or coin number 3, which has a value of number 5, what now? So now the question is, what is the minimum number of coins for sum 5? And we know that that is, okay, let me just, so the minimum for 5 is what? In this example, the minimum number of coins for sum 5 is
1.
Anyone? How many coins do I need to obtain a sum of 5 of the given coins I have here? 1, right? So I can just take this number 1 or third coin. If I add to it now this one over here, then we get the minimum in this case for a sum 10. Sorry, I'm losing again contact. Is going to be what in this case? 2 coins, right? This first one and this coin number 5. So the idea is that when we look at these actually sub-problems, minimum 5, minimum 7, minimum 9, and so on, these are sub-problems which we are using, that we've assumed to have solved previously, which we are using now to solve a larger problem, in this case, the minimum for sum 10. Okay, so this is just an example, and if we go back to these slides, this is what is written here, and you can have a look at this later on offline. So VJ is this value of the coin. We look at the minimum number of coins previously found for a previous sum. If this is M, then M plus 1. If it's less than the minimum number of coins we've already found, then we write that as a new result. So this is an example where we're using this solution to a smaller problem to find a larger problem. Okay, here we have this code written out. And again, you can go through this on your own. What we're saying here is, okay, I don't have to go through this. I think that you can again go through this on your own. And these are the examples, or the coin values added to the smaller sum, and you can try this out and see if you can obtain the same values. Okay, let's look at the problem at the knapsack problem, which again we're all familiar with, where we have a certain number of objects. We have a knapsack with a certain capacity, and we're trying to pick the optimal set of objects, which will maximize the value, but will remain within the weight, or the weight capacity, or the knapsack capacity, given the weights of the different objects. So we have assigned the values of the objects, we have assigned the weights of the objects. Let's look at, before I go on, let me go back over here. Let's look at this knapsack problem. So let's say I have, I have 6 objects that I have to decide on. Okay, and let's say that over here I have shown the objects which I've chosen so far. Over here I have objects which I still have to decide about, so I haven't picked anything yet. If we start branching with this problem, we can get something like this. So let's say first I take object number 1. What can we say about object number 1? Either I choose it or I don't. So if I choose it, then I follow this branch to the right. If I don't choose it, I follow this branch over here. So if I haven't chosen, I decided that I'm not going to pick object 1, then I'm over here. Okay, so I haven't picked anything yet, and now I still have to decide about objects 2, 3, 4, 5, and 6, right? If I take the second object and I decide I'm not going to pick object 2, then I'm over here. So object 1 and 2 have not been picked, and I still have to decide about 3, 4, 5, and 6. If I choose object 2, then I haven't picked 1. I decided not to pick 1. I have picked 2, but I still have to decide about 3, 4, 5, and 6. Okay, and so on and so forth. So we can branch in this way. If I keep going, how many branches am I going to have if I have n objects? Okay, so I have 2 to the power of n. Sorry?
2 to the power of n.
So 2 to the power of n. Okay, so I have 2 to the power of n, which is unacceptable. So we need some kind of a better way to do this or solve this than this kind of backtrack search. Each node actually represents a partial solved problem. If we look at it like this, so if I already chose object 2, and let's say it has a weight of 1. So this is the weight of object 2. If 2 is chosen, the remaining capacity, so if let's say my overall capacity was 13, this is the example from the slide, I chose object 2, which has a weight of 1, my remaining capacity is 12. We forget the original capacity. What can we do now? So we can, what kind of a problem can we now formulate? Anyone? Okay, so we're actually now, we can define a subproblem, or that is the same type as our original, but it's an independent problem. So we have a new knapsack. It has a capacity of 12, and we have available objects 3, 4, 5, and 6, let's say, that we can choose from. So we can define a new problem which is independent, as I say, and use it to help us find an optimal solution to the original problem. Okay, let me go back to the slide. So we define this procedure, KC1, which will return the maximum value that can be obtained if I have this capacity C, and considering only objects from I to N. So I is going to be 1, 2, 3, 4, 5, 6 in this example. So if I have 6 variables, if I'm considering, so my original problem would be 13, K of 13, 1. So my capacity is 13, and I'm considering all objects from 1 onwards. So I still haven't made a decision about the first, second, third, fourth, fifth, or sixth object. N is equal to 6. Okay, so this is, I'm defining this general procedure. Now, if I write it out like this, that would be my original problem. Now, if I decide that the first object is not chosen, now I continue. I've decided not to choose the first object. Now I continue with the second object. I get this procedure, right? I haven't. My capacity is still full. I haven't chosen any objects, but now I'm considering objects from 2 to 6. In this case, if the first object is chosen over here, then we reduce the remaining available capacity. And if I go back one slide, the first object had a weight capacity of 4 over here. So its value is 5, but its weight is 4. So we subtract 4 from this original capacity. I have 9 left, and I still have to decide about the remaining 2, 3, 4, 5, and 6. So 2 onwards, right, objects. Now, if I take object number 2, I haven't picked it, so I still have my capacity of 9. And I'm deciding about objects 3, 4, 5, and 6, or I did pick it. It has a capacity, has a weight of 1. My capacity is reduced to 8, and so on. If I keep branching like this, what we notice is that these procedure calls there are procedure calls which are repeated, such as this K9, 4, and so on. Once a sub-solution is found, we don't need to solve this given subproblem again. So in each iteration, we solve a new and independent subproblem, and we memorize or keep track of subproblems which we have solved so that we don't need to solve them again. So we have subproblems which are of the same type but are independent of the original problem. Okay, if we look at it just in terms of pseudocode, this is our procedure. So our function is going to return this optimal solution. If I is greater than N, so that would mean that we've already decided about when we return 0. So it means we've already decided about objects. I can't choose any new objects. Otherwise, so if C, so the remaining capacity, is less than the weight of the current object I'm trying to consider. If it's greater than, or sorry, if the weight is greater than, so we cannot consider that object because it's too heavy. So if I have a remaining capacity of 10 and an object which has a weight of 13, then we skip it. Okay, so we cannot choose that object. But let's say that it's then we keep going. Otherwise, let's say that we can consider the object. Then we return the maximum of one of these two things. So either we, oh, sorry, my phone is ringing. Hold on. Sorry, I forgot to turn it off. Either we choose object I, or we choose object I, or we don't choose it. So we need to decide. If we don't need it, then we keep going. So the capacity remains what it was, and we go on to the next object. Otherwise, if we did pick object I, then we add its value. So we add the value of object I, and we solve a new subproblem where now this capacity is going to be reduced by the weight of object I, and we continue with the next, deciding about the next object. Okay, so that's pretty much what we had illustrated on the previous slide. Once a subproblem has been solved, as I said, the solution is stored and can be looked up if, again, we come to that same subproblem. So we stored the solutions to recursive calls. The complexity is going to be much less than 2 to the nth, and that's the point. So we want to be able to reduce the complexity as compared to, for example, the initial simple backtrack search that we had. Okay, so this is an example of formulating these different subproblems that are independent and of the same type as the original problem. As another example, okay, so when we in general, when we talk about dynamic programming, and before I go on to the next example, we can look at it, as I said, from this bottom-up approach, so systematically solving all sub-problems that could conceivably be needed, or we can use the notion of memoization, which I'm sure you've heard of, or sometimes also referred to as a top-to-bottom dynamic programming approach, where smaller instances are solved only when they're actually needed. It's a similar concept, but sometimes one technique is more applicable than the other. Let's just look at a simple example of the Fibonacci sequence, for those of you that haven't seen this already. So let's say I have the problem of trying to find the nth Fibonacci number. In this case, I have, so this is the nth Fibonacci number, f of n minus 1 plus f of n minus 2. If I write out the program like this, what I see is that we start repeating certain calls. So f of 5 is equal to f of 4 plus f of 3, f of 4 is equal to f of 3 plus f of 2, and so on. And we get actually exponential complexity. What we can do is use this concept of memoization, which will give us actually linear complexity, where each state will be solved only once. So if we haven't found f of n, then we take f of n minus 1, or we store fib of n will be f of n minus 1 plus f of n minus 2. But if we've already found this solution, then we won't, or the solution to the subproblem, then we won't need to repeat it. Okay, so this is the notion of, as I said, trying to decrease. In this case, we will get linear complexity at a constant number of operations. Okay, going back to the slides. Okay, one more, or actually two more examples. Let's see how we're doing on time. Two more examples that I wanted to show you. This stagecoach problem is an example that was specifically constructed to illustrate the features of dynamic programming. What it's, the whole story behind it is that we have some kind of a fortune seeker going from, let's say, the state of, I think, Missouri in the US, going west to find gold in California, and has to find the cheapest path from going through the different states. Actually, what we're trying to do is trying to find a shortest path, but we have a specific number of stages that we can define where we have to take certain decisions. So we have stage 1, stage 2, stage 3, and stage 4. So we can actually illustrate it like this. So if I'm in stage A, or in state A, I can go to either B or C. From C, I can go to D, E, F, and so on and so forth. The idea would be to try to formulate this as using this number of stages and using dynamic programming. And to start with a smaller portion, actually, of the overall problem, find the optimal solution, and gradually enlarge the problem. What we're going to do for this problem is we can start with going from actually the end here, so from decision number 4, where we've almost completed our path, and we have one more step to go, and then start to increase the number of stages as we go along. Okay, what are the possible transitions between the different stages? So if I'm in A, I can go to B or C, and these are the lengths. If I'm in B or C, I can go to D, E, or F. And so on. So this is just from taken from the previous picture, and the final stage taken at decision here is if I need to end at the last node. So I can get there from G or from H. There's a whole bunch of now slides. I'm going to just quickly show a few of the slides, but then let you go through them offline. But what we want to say is that we have four decisions we need to make, or steps or phases. Let xn be the destination, so 1, 2, 3, or 4, the destination in the nth decision. So we describe our path as being A, so I start with A, I end with I, and now I need to get from A to I. So going from A to a certain node, we'll call that x1. So that will be our decision, or our destination in the first, let's say, step going back. So that's going to be either B or C. Then from there, I have to decide where I'm going to go next. That's going to be x2, x3, and then our final decision will always be, so we have already defined our final state or final destination. So an example path would be to go from A, C, F, H to I, in which case x1 is C, x2 is F, and so on. Okay, if we denote or use Fn, or to represent the shortest path from a certain node S to the n node, if the path goes through this node xn. So assuming that we have we've arrived in S in the n minus first step, and now if we decide to go if our nth decision is to decide to go to xn, then f of n is going to be the total cost of the best route for the remaining stages, given that we are in state S, ready to start stage n, and that we select xn as the next immediate destination. Okay, so I think the actual formulas and so on maybe are a bit confusing. The easiest is if we just run through the example, and then you can look at the formulas going back after having gone through the example. But let's use xn star will be the value of xn that minimizes our function. So that's our optimal, our best solution. And fn star over here of S is going to be the corresponding minimum value. All right, I'm going to skip now these formulas. As I said, we can get back to them later on. I just want to go show you, just to illustrate the example. Our objective is to find the shortest path, and what we're going to do is actually work, in this case, from bottom up, starting with the smallest subproblem and then expanding. So we're actually going to start from stage 4 and work our way back. Okay, so let's look at decision number 4. If we're in the 4th decision, the path is uniquely defined, so we know we have to go to state I. So we're here. We have to decide which of these two we're going to take, which path, and we're going to take the minimum. So the minimum of the value or the path that it took us to get to here, plus 3, or the minimum that it took us to get to H plus 5. Okay. So in decision 4, if we're currently in G, it's going to be so our next if we are in state G, the best way to get to I, or the only way, is going to cost us 3. If we are already in H, then 5 is our cost to get to I. Okay, so that's our decision in step number 4, assuming that we are already in G or H. Okay, now if we go back one step, now we're in decision 3. To get to G it's going to cost 2. To get to H, it's going to cost us 4. So that's parts of decision 3. Again, I'm not going to go through all of these, but what we know is that if I go from D to G, it's going to be this distance, so this 2, plus how long it took, plus I already previously calculated the best way to get from G to I, which was 3. Okay, that way we calculated that in the previous step. If I go via H, then that's going to be this 4 plus the 5 that I had previously already calculated. So I'm trying to find now the minimum of those two. Is it going to be this 2 plus 3 or 4 plus 5 that I had previously? Okay, so I'm going to take, so if I'm in D and going via G, then it's going to cost me 5. If I'm in D and going via H, it's going to cost me 9. The best solution would be to go via G, and we'll write that down, and that's going to cost me 5 altogether. So going back over here, it's going to be these 2 plus the remaining 3. Okay, if I'm in node E, so this is part of decision 3, to get to the final destination node, it's going to cost me 6 to get to G plus whatever we already previously calculated, or 3 plus whatever we previously calculated from H. Okay, again, that's written out here. And we know that's going to be, if I go via G, it's 9. If I go via H, it's 8. So I decide to go via H. And what we're doing actually is we're writing out these different steps that tell us if I'm in node D, my best solution will be to go via G, as the next step will be to go via G, and from that point, from D to the destination, my total trip is going to be 5. If I go via E, I have the best way to go from there is via H, and the best solution will be 8, and so on. And okay, I'll skip through this. If I'm in node F, doesn't matter, so I can go either via G or via H, and the cost is going to be 6. So now we know in stage 3 what would be the best way to go if we're in stage 3, depending on where we are. And we keep going, and again, I'm going to just flip through these slides. So in stage number 2, again, I'm already using this information which I've previously calculated for stages D, E, and F, and so on. So the whole point of this example is to illustrate that by calculating the different stages or the shortest paths in the different decision points, we can use this information to solve this overall shortest path problem. Okay, so again, this is, I'm just going to click through this now. This is all the same different steps. You can look at it at the slides offline. Just to get to the first decision, so decision point number 1, where then I decide whether to go to B or to C. I know that if I'm in B, from B onwards, the path is going to be 10. If I go to C, from C onwards, it's going to be 8. Okay, so in this case, then my overall path, if I go from A to B, is going to be 11. If I go from A via C, it's going to be 10, and that will be then the optimal path. Okay, so the optimal solution, optimal path length will be 10. And if we write that out, we can see that the decision, we can follow this path and find the best decision points going from A to C, C to D, D to G, and G to I. Okay, so that would be the optimal solution. I went through this very quickly, but again, you can look at the slides offline. The point is that we can divide the problem into phases or stages, where we have a sequence of interrelated decisions. Each stage has a certain number of states. And again, going back to this optimality principle, when we are in a given state, the optimal solution to subsequent decisions only depends on this current state. It's independent of the previous stages. So the different subproblems that we are defining are independent of each other, and that's an important characteristic. So we can define this recursive relationship where we calculate the optimal solution in stage n given an optimal solution for stage n plus 1. So this was just a different example where, compared to the previous examples, where we start with this n plus, or start with the final solution and work our way backwards. Given that we are now short on time, so it's already 4 o'clock, there is one more example here which you can look at, and I'll go through it very quickly next time, and also go back to, so I said I'll upload the example LP problem formulation. I'll also upload an example branch and bound problem, which is something that typically you might see on the midterm. So just so that you can have a look, and then we can go through that quickly in the beginning of the next class. And you can also look at so there's an example given in these slides of finding or using Floyd's algorithm for finding all the shortest path between all pairs of nodes in a directed weighted graph, and how dynamic programming can be used in this case. So I'll go through this example next time. But the idea is that the procedure is constructive. We're moving backwards through the stages until the optimal solution is found. Okay, so for next time, as I said, go through the remainder of these slides, and then we'll go through that together. Also, try to formulate the LP problem, try to solve the branch and bound problem that I will also give you, and that's pretty much it for now. There was a comment, so I'll also upload the slides for the next lecture prior to, so maybe a day or two before. I just have to finalize the slides prior to the next lecture. Okay, are there any questions? Okay, let me just stop then recording.